Hello, my name is Christina Shryock, and today I will be talking about the valence bond theory of the nitrite ion. So first, what I like to do is first give the Lewis dot structure of nitrite. So nitrite is NO2 minus, and we know that nitrogen has 5 valence electrons. Oxygen has 6 times 2 plus one electron that you get from the minus. So that's going to equal 18 electrons. So then I'm going to put nitrogen as our central atom and oxygen, the two oxygens on the outside. And then what I like to do is I like to count. So this is 2, 4. So we start off with 4 electrons, and then we're going to need 14 more to fill everything in properly. So I like to do 2, 4, 6, 8, 10, 12, 14. And so now we see that nitrogen is not at a full valence yet of 8. So I'm going to take this oxygen, this lone pair of electrons, and bring it down to be a bonded pair to make an octet for both oxygen and nitrogen. So once that's done, then you can't forget to put your brackets around your Lewis dot to signify that negative, which makes this molecule an ion and have a charge of -1. So now by looking at our Lewis dot structure, we can see that there are going to be 3 electron groups. So this is going to be the first, second, and third. So knowing this, 3 electron groups means means that the electron geometry is going to be trigonal planar. This is the electron geometry. However, knowing that we have this lone pair right here, the lone pair changes this from a trigonal planar. The molecular geometry is going to change due to that lone pair. So now the lone pair, because now the molecular geometry, because of the lone pair, is going to be bent. Now this is bent due to the fact that lone pair to bonding pair repulsion is going to be greater than bonding pair to bonding pair repulsion. What this means is that lone pair on the top of the nitrogen atom is going to slightly bend everything down, all the oxygens and their electrons, because they are repulsing each other. They do not like each other. They do not attract. So that's what's going to create the bend in our VSEPR structure. So now we are going to do the actual VSEPR structure. So from previous, we've learned that our VSEPR structure is going to be shaped as the molecular geometry of the bent shape. So it's going to be bent usually, like, as a rough sketch, looks like this. So that's how it's basically going to look like when we add our our very own molecule in. So nitrogen is going to go on the top because it's the central atom. And then we're going to have the 2 oxygens. Let me make this line a little straighter. It's going to be the 2 oxygens. And we also have to remember that one oxygen does have a double bond. So we need to make room for that double bond. It's important that you also remember to show that in every step that you do, because it's important to show all the electrons and also the brackets as well. So this is going to be the Vesper shape, the molecular geometry of this ion. And we also want to show that the bond angle in this certain ion is going to be right here, and it's going to be less than 120 degrees. This is going to be due to the fact that lone pair to bonding pair repulsion is greater than bonding pair to bonding pair repulsion. Okay, so these are what the images of this specific molecule is going to look like. So remember that our molecule is NO2 minus. The blue atom is going to be nitrogen. These are the 2 oxygens. And remember, we do have a lone pair right here. And then right here we have 2 and 6. This is going to be our sigma bond. And then we have another sigma bond right here. And then that top bond, because it's the second bond, it's going to be a pi bond. This is also going to be our bond angle of less than 120 degrees. So that's going to show you the ball and stick way image. And then this is more of the contour. The second image is more of a contour diagram. This is going to show you right here's the nitrogen, oxygen, and oxygen. This is going to be these 2 bigger pieces are going to be the pi bond. And then we also have a sigma bond right here and a sigma bond right here to show you same thing. This is just 2 different ways of showing one ion. This part of the image and this part of the image is going to show that this molecule is hybridized. It's going to show the hybridized portion of the molecule, which in this case for our molecule, the hybridization is sp2. We also just have to keep in mind that for the bond angle to be less than 120, it is because lone pair to bonding pair is greater than bonding pair to bonding pair repulsion again. This last image is also another way of showing our molecule. So for this, this would be our nitrogen and then our oxygen and our other oxygen. This is showing the lone pair on the top of nitrogen, as well as we're going to have a single bond and then a double bond. So the single bond right here will represent a sigma bond, another sigma bond for the first bond right here, and then a pi bond for the second. Again, this is going to be a bond angle of less than 120 degrees. Our molecular geometry is going to be the bent shape, but our electron geometry is going to be trigonal planar. And then just not forgetting that around this whole image, if we were to draw it like out, there would be brackets around it because there is a charge of -1. Now we're going to do the box diagram for nitrite. So first, for this, you just look at the central atom, which is going to be nitrogen. When you're naming what the ground state, the excited state, and the bonded state, you use the nitrogen. And so what we're gonna do is look at the periodic table and see if the s orbital is filled. So it's filled, that one has 2, and then in the p orbital, nitrogen has 3 electrons. So since this is already filled, halfway filled, we know that there's not going to be an excited state in this particular, there's no excited state in this particular case. So we're going to skip that part and go straight to hybridization. So right here, we're going to do an arrow and it's going to say hybridize. So now we have to remember that hybridization for nitrite is going to be sp2. So the hybridization for nitrite is sp2. So that's going to be right here in the middle of 2s and 2p. So then we look at what's going to be hybridized, and we know that these are going to be hybridized. So then we write them over here. So I'm going to do 1, 2, 3, and then since there's 1 left over, it's going to be in the p orbital. I'm going to put 2p right here. So then to complete this, we're going to look at the oxygen, our 2 oxygen. So I'm going to do the first oxygen up here. And we're just going to look at their p orbital. So p orbital has 3 little slots. I'm going to put 2p, and for oxygen, the p orbital has 4 electrons. So 1, 2, 3, 4. So then we know that this is gonna bond with this one. This is gonna bond with this one. And this is gonna make our 2 sigma bonds because they're bonding to the hybrid orbital. And then we're gonna look at our other oxygen. I'm gonna put it down here. So same thing, has 4 electrons. So 1, 2, 3, 4. And so we're gonna see that this is gonna bond with this one, and this is gonna bond with this one, making the pi bond right here, because it's with the 2 left over p's and it's not bonding to the hybrid orbital. So that's gonna be our bonded state for nitrite. And then we're gonna, just to make sure, we look back at this. And we see that here's the sigma bond, and a pi bond. So for the contour diagram for nitrite, the first thing that you do is write out your reference lines. So these reference lines just kind of represent that it's trigonal planar bent. And then we add this extra line because they have to represent the lone pair on nitrogen. Okay, so first thing that you do, you're gonna write out your N in the middle for nitrogen, and the easiest one would probably be for nitrogen just because it just has a lone pair. So you're gonna write sp2 and the lone pair. Now for the first oxygen, same thing, sp2, and this one is gonna be for the one with just one bond. So we're gonna write the p orbital, which is like an infinity sign. And to show that these are bonded, I'm going to change this color to a different color so you could see it better. We put these two electrons. This is going to be like the electron overlap to show that they're bonded. And we're going to write right here 2p, and this is an oxygen. So now we're going to do the last oxygen, which has the double bond. So first we're going to start with the sp2. Let me make that a little bit bigger. And then another one. Show the electrons to have that bonded state. Then we will write oxygen. This is the oxygen. And then we're gonna go over to the pi bond. So right here there's gonna be a pi bond to represent the double bond, and it goes with the N. The pi bond is from N to O. That's how it would look. I'm not drawing the other side. So we're gonna do the one electron down here, up there, and a one down there, and show these lines to represent that they're connected. I'm gonna write pi. Right here we have the sigma bond, and right here another sigma bond. So that's all three of the bonds represented, and the last thing we're gonna do is represent the two lone pairs on this oxygen. And put their electrons. So then after all that, we're gonna do the brackets. And then our bond angle, which is less than 120 degrees again. And just a little note right here that right here for this bond is going to be greater than 90 degrees. And that's it for this video, and thank you so much for watching.